Welcome back.
Hi everybody, welcome back.
Hi.
We are ready to finish out lesson 1.2.
This will be shorter than yesterday,
much
promise.
shorter, but it's still got some very important vocabulary, so we want to give it its own day.
Okay.
Alrighty. So first thing we need to talk about was we left off last class with symmetry. We were talking about even versus odd functions, and today we are ready to go forward with that. There's a couple of different things you need to be able to do. You need to be able to just identify graphs. That's what you did last class.
Last class, that's what we did.
Today we're going to focus on proving.
And this is really that algebraic idea.
Okay, that's not a geometry 2-column proof, but it is an algebraic proof. And they are important the higher you go in mathematics, so you want to get it right now.
And you have to be able to do all the steps, not skipping anything, one thing at a time. And there's a proper way to do this, and then there's a wrong way to do this. We're going to show you the proper way to do this.
Okay, so again, let's remember our rules for even versus odd functions.
Both of them started off with f of negative x, or f of the opposite of x.
Which means,
we're going to actually plug in negative x into our function.
okay, because that's what the function notation says.
For an even function, after we're done simplifying, we should get f of x, or the exact same function we started with.
The same y value, the same function.
Notice we're not plugging in numbers now, we are plugging in x's. For an odd function, we will actually get the opposite of the function we started with, which is be like multiplying the entire function by -1. Okay, so we're opposite of the entire function. All right?
Okay.
That's our goal. Let's do it.
We are ready for the next.
No,
I'm pushing the wrong button.
backwards.
Okay. All right, so let's look at letter A.
So what's
We
the first
need to,
step?
Again, check the directions. You want to prove whether it is even, odd, or neither. So neither we'll get to in just a second. F of x equals 5x squared plus 5. First step was to plug in a negative x. So let's just do that. Everywhere you see an x, in Algebra 1, I like to tell them to make a little home.
Absolutely. If you put a parentheses around everywhere there's an x, you really are going to have a harder time screwing this up,
Okay.
which is a good thing.
That's a good thing. So I'm going to put a negative x everywhere you see an x.
Okay.
Okay, the second step is simply to follow the rules of algebra.
That's the hard part for some
Okay.
people.
Do we know any rules of algebra here?
We can square negative x, which is really just minus x times minus x, which is positive x squared.
Okay, so something mathematically happened there. We didn't just magically make the negative go away.
Yeah, we don't just throw negatives around.
Okay. All right, once we are done simplifying with the algebra as far as we can, we want to compare.
Compare it
let's
to our original function.
compare to the original. What do you notice?
Well, that looks exactly the same.
That is exactly the same as the original function, is it not?
So f of minus x then, continuing from the left side, is actually equal to f of x.
It is. But wait a minute, that was our rule.
That's a rule for which function?
That was a rule for an even function. So
What do
from
those three
science,
dots mean?
I stole that notation. It means therefore.
Therefore, I like it.
F of x is even.
Please, this is writing a mathematical sentence and a proof, and all these minus signs and these f of x's, they all mean something.
And nothing can be left out. So you should
Nothing.
have the first part of the proof, the very first step, plug in a negative x, and we should explicitly see there's no simplifying, no skipping steps here. Plug in
right
a
in.
negative
It's a
x
proof.
every
It's-
time you see an x.
You're not trying to convince anybody, you're trying to prove it one step at a time.
Okay? Then you need as many steps for algebra as you need to simplify it as far as you can.
That might mean 1 or 2 or 3 or 4 steps, depending on how
might.
many x's are there.
The third thing you need to do is then compare. Okay? And you're going to compare it back to the original. When
It's
you
either
compare
going to equal the same,
Yep.
it will either equal the opposite of the same function, so it'll be minus f of x, or it could be something totally not the same.
At all. Not related at all.
Not the same, not opposite, and what does that mean?
That would be a neither.
That'd be,
Okay.
There's a lot of functions out there that aren't either even or odd, aren't
Absolutely. And a lot of students mess up because they assume, once they find out something's not even, they assume it's odd. It's not an absolute. There's 3 choices here.
there? Right. It's
Okay.
even, odd, or something else.
Something else.
And there's a lot of those something else's out there. So.
Okay. So, Mr. Lucky, you want to give him a try with letter B?
All right, we'll try with letter B here.
Okay.
Okay. So the first thing we're going to do is what?
We're going to plug in a negative everywhere we see an x. We're going to find g of negative x.
G of negative x is going to equal x squared plus 8 times that something.
Plus 12.
And what
the
goes in
something
there?
is a negative x. Okay. Now we're going to do some algebra. Well, I know from algebra that negative x times negative x is positive x squared.
Okay.
And I know from algebra that positive 8 times negative x is negative 8x.
Okay.
And I can't do anything with a 12, so I'm going to put plus 12. We're kind of done with our algebra step. Now we need to compare. Okay? So compare. Is it the same as the original? Well, there's 3 pieces here. So when we say the same, it has to be exactly the same. All 3 pieces have to be the same.
That one's
Yeah,
different.
The one in the middle is different. Okay, well, is it the opposite of the original?
No, because if we did the opposite of that whole thing, it would just be like In other words, if I wrote minus g of x up here, just for fun,
Right.
just to see what it would look like, that would be minus 1 times that entire thing.
So it'd be negative x squared.
Negative x squared minus 8x minus 12.
Okay.
And it doesn't look like that either.
It doesn't look like that either. So here's what we figured out so far. Go ahead and let's write a statement here. We figured out that g, my writing's terrible, sorry, of negative x is not the same. We need to see your thought process. This is the only way we know how to do it. We also figured out that, excuse me, g of negative x is not the opposite of g of x. Okay?
Therefore,
Therefore,
g of x, our function we're using,
okay,
is neither
it's neither.
even, is it nor, odd,
it is.
neither nor, either nor, neither nor.
Make him stop.
IR math teacher.
I would have just said neither and put it stopped there. Okay? So that's what a neither looks like. We have to see, we can't express enough that we have to see this statement along with this statement.
Yep.
We need the algebra and the words for you to receive full credit. Okay?
You getting it?
No surprises here. We're telling you exactly where you're going to get marked off, and we don't want you to get marked off.
No, we want to give you full credit.
Okay, so symmetry continued into proving to even and odd. What else do we need to cover?
More vocabulary.
Okay.
Let's start with some vertical
Vertical
asymptotes, okay?
Well, we mentioned these the other day. That was that vertical line that you get closer and closer to.
Yep. So let's do this. Let's pull up a calculator, and
Okay.
hopefully it'll actually pull up.
There it is.
We're going to graph the function 1 over x plus 3. Now,
Okay.
we brought it up here just to reinforce the fact that you have to type this incorrectly. When you have more than a single term in the numerator or denominator, you have to put parentheses around it. Now, notice
Absolutely.
we don't have one around the 1, but if you did, it wouldn't be wrong. Okay,
Yep.
but we're going to graph this thing, and we're going to graph it. If you don't see that, press zoom 6, and it will re-zoom your window back to a normal standard window.
Okay.
All right, so what happens to this function at x equals negative 3? That's the question that's being hidden behind our calculator
Well,
right
when
now.
x equals negative 3, the right side of the function goes shooting up, and the left side kind of goes shooting down.
So we basically have a vertical
We have a
asymptote.
vertical asymptote. Yeah.
So why do we have a vertical asymptote at x equals negative 3? Why? Well, right now, other than looking at the picture, the best explanation we'd like you to give us is for you to show us that if you plugged in negative 3 into your function, what do you get?
you should get undefined.
You get 1 over 0, don't you?
Yeah. you
Didn't
do.
we talk about earlier you're not allowed to divide by 0?
We did. That was we had to take that point out of our domain.
So we write our domain basically said x could not be equal to negative 3. We wrote it as interval notation.
Correct.
But if we plug in negative 3, we get 1 divided by 0, which is why this is undefined.
So vertical asymptotes happen because you take something in the numerator and try to divide by 0
By
in the
0.
denominator.
By
Okay.
0. Something that's not 0.
Okay.
All right, so let's try the next one, just to see how it compares.
Okay.
All right, we're going to take x squared minus 9 and divide it by x plus 3. So again, what we're going to do is we're going to have this function that we want to divide, and then we're going to put it in parentheses. And let's go ahead and insert
X squared
x squared.
minus 9. I think your head's in the way. Yep. Minus 9. You're typing over.
Oh, well.
Okay.
Divided by, and then another parentheses, x plus 3. The insert didn't work because I had to go back and correct some plus sign. But anyway, now we have our function, and we're going to graph it.
So now again, we would expect that since it's x plus 3 in the denominator, maybe a vertical asymptote. But we know that it can't be in the domain.
Our domain was still x cannot be negative 3, correct?
Okay, but Mr. Lecky, I see negative 3 on the picture.
Huh. Well, let's try something here, shall we?
Okay.
Our calculator has the ability to calculate a value.
Yes, because that's how it makes a graph.
So if we go second calc, which is second trace above.
Oh,
that is
value,
calc,
it's right there.
It's value. So if we hit enter,
Okay.
it's going to ask us for an x value.
Well, negative 3.
Let's plug in negative 3.
Okay.
What's the y value when x is negative 3?
Where's the y? There is, it won't write on the calculator, but there is no y there.
There's no y. Well, why not?
Because it doesn't exist. It wasn't in our domain.
Well, let's try this for a minute. Let's plug in g of negative 3.
Okay.
Because it's obviously not a vertical asymptote. Would you
Right,
agree? Based
right.
on the picture?
It's not.
If we plug in negative 3, we get 0 on the bottom. We've established that from the prior
We do.
example. But what is negative 3 squared minus 9?
Well, negative 3 squared is 9.
So 9 minus 9 will give you 0 as well.
Oh.
Ooh, now we have a problem. 0 over 0 does not give us a vertical asymptote.
No.
It actually ends up giving us what we see in a picture. That picture is actually just a line with a hole in it.
That's a removable discontinuity.
It is. So this is going to give us a hole at x equals negative 3 as opposed to a vertical asymptote at
Okay.
x equals negative 3.
So this is where pre-calc is different. We are building on the vertical asymptote concept. We are relating it back to domain and range because it is the same stuff. And we want you to know the difference between a vertical asymptote and a hole,
That's
or
important.
removable discontinuity.
For this is extra
Okay.
credit for those of you. This is where we're going. Remember x minus squared minus 9 could have been factored?
Difference of squares.
We are going to remove the discontinuity
Cancel.
by canceling them, and we get a function that is really just x minus 3, which is just a line,
It's that line.
but we've removed a point, creating a hole.
Very nice.
Okay, that's for later.
It is.
We're trying to get you there just to kind of give you a taste of what's coming much later in the course. Well, next chapter.
Okay, so let's summarize this in our little box here. Vertical asymptotes occur in rational functions when
Keyword rational functions. We'll get to that later.
rational being a fraction.
When you have a non-zero number divided by 0, so
Number divided by
number
zero.
divided by 0.
Okay, but if you plug a point into your function and you get 0 divided by 0, you should look for removable discontinuity or a hole.
And for those of you watching this, this is a non-zero number if we want to be technical.
Oh,
Okay?
he's being calculus again.
I get emails from people who watch this that they tell me that we did something wrong. Okay, it's just a
Non-zero.
non-zero number. Okay, divided by 0.
Okay,
Got it?
I think that's about it for vertical asymptotes.
All right.
Okay, next topic is end behavior. We're not really sure how familiar we are with end behavior, so we're just going to jump right in. We should have covered end behavior in Algebra 2 and FST. We talk about as x goes to plus or minus infinity. We talk about the
That's
ends,
way
what's
right or way
going
left?
on as x gets really big.
Is this
Okay?
more like this?
Yeah, it's like a little swim. Okay, so we're going to be doing end behavior with a graphical approach for right now. Again, back to those rational functions. We'll deal with those in a later chapter.
And we're going to eventually try
Okay.
to do this without a graph, but
We will. We will do it without a graph.
that's
Okay,
a go.
so for right now, we're going to describe the end behavior of each of the graphs shown below.
Now,
So
I remember from Algebra 2 there was a sentence I had to write every time.
there was, and we kind of just memorized it. As x goes to infinity, f of x does something.
And can I write this some other way?
No,
No.
that's it.
So this is our way to... Don't create your own version of this sentence, okay? I've seen them all, and they all get marked wrong. We are going to go to the right, which is x going to infinity, and then we're going to look at the y values, f of x. So as we
So-
go to the right, where does f of x go?
There's our infinity. What is f of x doing way over here? It's going whoop,
Going way up.
way up.
So that's plus
f
infinity.
of x is going to infinity. Okay. As x goes to negative infinity, there's a negative there.
So as we go to the left,
f of x is still going way up.
it still goes up.
Okay. All right.
This
let's
is her.
Check the one in the middle. They don't know that yet.
I know.
Some of them do because they had me last year.
They're laughing right now.
Okay. So this middle graph here, as
As starts with an
I'm
A.
going to start that again.
All right.
Make it stop.
Excuse our technical difficulties. Oh,
My
that was a capital
technical
A.
difficulties.
As x goes way to the right,
What is the f doing?
well, it looks like it's going up again.
It is going up, but Mr. Lucky, does it matter it's doing all this stuff in the middle?
Nope, because that's not infinity. We don't care what happens around
We don't
0
care in the
or
middle.
10 or even 100. What we care about is what's going on as x goes as far to the right as possible.
As you can imagine.
How about as x going to negative infinity? That would
Okay.
be way to the left.
F of x going down.
f of x going down
And going down is?
negative infinity.
Alrighty.
That was fun, wasn't it?
Okay, I'm going to make you do the last one because I can't write that small.
All right. Let's try this. We're going to go to the right again on the x-axis. Where's
Okay.
our f of x going?
Up. So as x goes to infinity, f of x goes to negative infinity.
f of x is going way up.
Oh, yeah, up. Infinity. I don't know what I'm saying.
Did you say negative?
I did.
Don't do that. Okay. All right. How about as x goes to the left?
To negative infinity. That's the negative I was thinking of.
All right. Well, as x goes to the left,
That's kind of just
my
going across.
y values aren't really changing. What is that number? It's about negative 3, isn't it?
It is about negative 3.
All right. So how about we say that f of x
Oh.
is going to negative 3?
So we can go to a number. Hey, it's bounded below.
Weird.
That's pretty impressive.
All right.
Okay.
Okay. So does it always have to go to positive or negative infinity?
No, it doesn't. It could go
No.
to a value.
It could go to a number.
Okay. And again, there should be some review, especially if you had Algebra 2 last year and came straight into pre-calc. FST people might not have had as much practice with it. Okay,
But hey, you
but
got to do something new eventually.
we got to take it to the pre-calc level now. So go ahead and go to the next slide, Mr. Lecky. So let's get this into some pre-calc level here.
All right. In fact, we're going to take it all the way to the calc level.
Ooh.
I know you don't like writing
I'm
this
scared.
sentence. That as x goes to infinity, f of x goes. People don't. I don't know why, but I get all kinds of weird stuff. I don't know about you.
I do.
Let's come up with another way to write this. Well, we didn't
We don't have
invent
to
it.
come up to.
We're going to just use it. Is that
We're
okay?
going to use it. We're going to start using limit notation. And this is so that when you get to calculus, you're at least familiar with the notation. You're not familiar with all the nuances of what a limit is, okay? But there's some specific notation that you should get used to. Okay, Mr. Lecky's giving us a box tour here.
If you were going to just plug some things in,
Very nice. Where is x going?
this would be what you have. You have the word limit,
Okay.
and right below it, it's going to say x arrow, which means x is going
somewhere.
somewhere. It could be a number. In our case, it's going to be positive or
Positive
negative
infinity.
infinity every time.
Okay, so that'll be the same.
All right. Then you're either going to write f of x for the function, or you can actually write the function if you know what it is.
Okay.
And then you're going to write equals. We're going to write equals.
Okay.
And we're going to talk about where f of x is going, or where y goes.
Okay.
Is that okay?
That's great.
That's really what we're doing. But there's a specific way to write it. It's like
Okay.
learning a foreign language and learning how to write specific symbols.
Okay.
Okay? You got to write it the right way. So how do we do this? I'll do one, you do one?
Sounds great.
Okay. So
I'm
let's take the
waiting for
first
you
one.
to show me.
All right, let's take the first one. As x goes to infinity, f of x is going where?
To negative
To
infinity.
negative infinity. We're going to take that statement and we're going to write it like this. The limit as x goes to infinity, or as x goes way to the right,
Okay.
the function f of x equals, or where does the y values go?
Negative infinity.
It goes to negative infinity.
Okay.
That's a lot shorter. Says exactly the same thing.
Okay.
Let's try the other one. What are we going to say here? We're going to say the limit as x goes, now which way is x going this time?
Negative infinity.
Negative infinity.
Okay.
The function value
F of x.
is going to go to
Infinity.
infinity.
Nice.
All right?
All right, I think I got it. Let me try.
All right, let's try this one.
Okay. Oh, wait, Mr. Leck, you forgot half the question. He forgets to read the question. The rest of the question says, sketch a possible graph for f of x.
Oh, forgot that. There wasn't enough room for that.
Oh. Grab it over there. You can,
Okay, you want me
what
to
do you
grab
wanna
this? All right.
Apparently, I can't.
I'll finish my problem. How's
Finish
that?
your problem.
So as we go to the right,
We have to go.
the y values have to
down.
go way down. So we have to go somewhere like this. Is that okay?
That's beautiful.
And as we go to the left, our y values have to go way up. So how about we just keep going
There you go.
and pretend they're connected? Okay? Is that good enough?
It's continuous.
All right. Perfect.
Okay. He finished his problem. I'm happy now. All right. So let's start with the first sentence. As x goes to infinity, f of x goes to infinity. So again, we're going to do the limit as x goes to infinity. And when you're writing this on paper, you can think of this as like a subscript.
Yeah.
Okay.
They're right on top of each other.
Okay. And then f of x is kind of like the same size as the limit part. Okay. And so I'm going to infinity. Does that look all right?
Wonderful.
Okay, let me try the other side. As x goes to negative infinity, f
You
of
want to
x
write below
goes
it
to
because you're going to have to draw a picture.
0. I can't fit it below it. I'll figure it out. And I always kind of make a cursive L. I don't know why. I just do. X goes to negative infinity of f of x. Now, if this was called g of x or something like that, should we put a g of x there?
Probably.
And if we knew it was like x squared, we should probably put an x squared there?
Yep.
Okay.
That would be better.
So as I go to the right, I need to go up forever and ever and ever and ever. Shoop. How about that?
Yep.
And as I go to the left, I need to go to 0. Good thing I didn't accidentally cross my 0, huh? And again, we're going to pretend like those are connected.
Okay.
Okay? So there's our limit notation. Now, some of you might be saying, and looking at this picture and saying, gosh, that looks like a horizontal asymptote.
Yeah, that's what it is.
Well, it really is. And we'll do a little bit more on that section in 2.7. But basically, we've cut down a little bit because we realized that lesson 1.2 is just gargantuan with 12 learning targets.
Huge.
So I think that'll do it for the second day.